Okay, in this problem, we're going to minimize inventory costs. So let's read it together. Foggy Optics Incorporated makes laboratory microscopes. Setting up each production run costs $2,500. So that's one cost right there, $2,500 for a production run. Okay, so I'm going to put that in my formula in just a second. Okay, then we know that insurance costs, based on the average number of microscopes in the warehouse, amount to $20 per microscope per year. So this is based on the average number of microscopes. That average word is going to be important in just a minute. And that value was $20 per microscope per year. Storage costs based on the maximum number, okay, that's an important phrase also, of microscopes in the warehouse, amount to $15 per microscope per year. So we have three costs so far. We have a production run cost, and then we have carrying costs, and those are the insurance costs and the storage costs. So continuing to read, suppose that the company expects to sell 1,600 microscopes at a fairly uniform rate throughout the year. Determine the number of production runs that will minimize the company's overall expenses. Here is our objective, to minimize overall expenses, and the overall expenses were listed at the start of the problem. So on the next page, let's set up our equations. So we have our cost equation, and that's our objective function, so let's establish that first. So cost is going to equal the $2,500 is for every run. So we're going to say 2,500 times R for run. Then we have two carrying costs. So I'm going to add to this 2,500 a cost of $20, and that $20 they told us is for insurance, and it's based on the average number of microscopes in the warehouse. So that number of microscopes in the warehouse for each, at the beginning of each order time, or at the when they're ordered, is going to be X. The average number, which is what this cost is based on, is half of that. That's your average number. So that's why it was important to focus on the word average. Okay, continuing with another cost, we have storage costs, and that's $15 a year, but the storage cost is based on the maximum number of microscopes present in the warehouse, and that maximum number we're going to define as X. So here, the first term, that was ordering costs. Here, the second term, that is carrying costs. So be able to distinguish between them. And its carrying costs you have to be careful of, because sometimes it's based on the average. This was based on average, that's how we express it. Sometimes it's based on the maximum. So you want to be able to write these correctly because all your work is based upon this. All right, our next equation that we have to write is the constraint. So this cost was my objective function. My objective is to minimize the cost. All right, so now let's put my constraint in green. So my constraint is that they want to sell 1,600 microscopes every year. So their run, the number of orders they make, times how much they have in each order, has to equal 1,600, and that's my constraint. So R is the number of orders placed a year, and X is the number of microscopes in each order. All right, as we always do, we're going to use our constraint, and since they want us to identify the most efficient number of runs, we're going to identify what R is. So in order to do that, I'm going to use my constraint, and I'm using my constraint to get another expression for X. So X is going to equal 1,600 divided by R. And I got that just by rearranging the constraint equation. Okay, we're going to go to Brown now. Let's write a modified objective function, and it's modified by reducing it to only one variable by using this substitution right here. So here's my cost. Cost equals 2,500 R plus 10, because, well, let's combine like terms first, because we can make this simpler. So let's focus for a second here. 20 times x over 2 is 10x. So this is going to be 10x plus another 15x. That's 25x. So I have 25, and instead of writing x, I'm going to write 1,600 over r. Okay, let's simplify this. C equals 2,500 r plus 25 times 1,600 is 40,000. So 40,000, and then let's bring the r up using our power rule. At this point, I'm ready to take the first derivative because we want to minimize. I want to know where the slope is 0 of this cost function. So C prime equals 2,500 minus, because I'm going to bring down the -1, minus 40,000 times r to the -2. In order to minimize it, the slope has to be 0. Set that expression equal to 0, and we'll continue on the next page. Okay, I've rewritten my first derivative, and I've brought my r squared to the denominator, and that's what made it go positive, so I should not have to explain that piece of it to you. Setting this equal to 0, I can do the following. 2,500 equals 40,000 over r squared. Do your cross products. 2,500 r squared equals 40,000. R squared will be equal to 40,000 over 2,500. Doing the math, r squared equals, this is going to be 16. So therefore r equals plus and minus radical 16, but because we're talking about the number of orders, it has to be positive, so therefore r equals 4. That's the number of runs that hopefully minimize my costs, but I am not done because I have to make sure that I have indeed found the minimum. So on the next page, we'll take the second derivative. Taking the second derivative, I get C prime prime equals 80,000 times r to the -3. So I can write it this way. It was 80,000 over r cubed. And when I put a positive number in for r, which 4 is a positive number, this will always be greater than 0. And so therefore, my cost function, is concave up, and the CV of r equals 4 yields the minimum cost. Go back and make sure you understand this, especially focus on your storage, your carrying costs, determining whether they're based on the maximum amount of inventory or the average amount of inventory. So make sure you understand how to create that cost problem, or that cost equation. And don't forget to always, always, always take the second derivative and check that you have indeed found what you wanted to find.